Okay, welcome everyone. Today we have our very own Dan to give us a CGD seminar. And well, I believe a lot of you are familiar with Dan, but I think I will just introduce him just in case somebody who is not familiar with him. Dan got his bachelor in math and physics from Columbia University in 2009. And then he joined the MIT Hui program in physical oceanography and graduated in 2016. From 2016 to 2019, he did his postdoc with the NSF postdoc fellowship at the University of Washington. Then he just joined NCAR CGD as a scientist one in the oceanography section. And his interests include ocean physics and dynamics, Earth system data simulation, and paleoclimate. Okay, without further ado, it's all yours, Dan. Thank you.
Excellent. Thank you very much, Young. Are we good on audio? Great. Well, thanks everyone for being here this morning, both in person and online. I'm excited to share some work for you that happened over the past few years here at NCAR with David Stevenson, who was a postdoctoral fellow, and in collaboration with Luann Thompson at the University of Washington. And this is work supported by a NASA physical oceanography project. And so what I'll talk today about is a procedure for discovering dominant drivers of ocean variability. And so an outline for the talk, first I'll discuss the origins of ocean variability, starting from a very broad perspective. And then go on to discuss dominant modes and pathways and sort of conflicting ideas or pictures that we might get when you look either from the ocean or the atmosphere. And then I'll try to reconcile these two different approaches with a new kind of dynamically weighted principal components analysis. And then from there, I'll use this to diagnose the dominant atmospheric drivers of heat content variability in the subpolar gyre. I'll show how using an ocean model, we can trace the pathways by which ocean stochastic variability, atmospheric variability drives the ocean. And then at the end, briefly also discuss an application to decadal AMOC variability. So what causes ocean variability in the first place? At a high level, we can think about quote unquote deterministic forcings. So the fact that the Earth goes around the sun and the moon goes around the Earth. So these sort of astronomical tidal forcings, anthropogenic forcings we might think of as being deterministic. Of course, both of those systems are maybe chaotic in their own right, but let's be satisfied with those scare quotes. The ocean varies in part because the ocean is a turbulent fluid, and so variations arise from the chaotic variability in the ocean itself. And then, of course, all of the things that we study here in CGD, this kind of menagerie of coupled Earth system processes of land interacting with the ocean, interacting with the atmosphere and the ice, the cryosphere components. And this can get a little bewildering, but we're fortunate to have what has proven to be a powerful framework for thinking about ocean variability, or at least a lot of it. And this arose famously now almost 50 years ago in papers by Klaus Hasselmann and Frankenmuehl that basically argued that a lot of the stochastic variability that we see in the ocean can be attributed to variability that arises from the atmosphere. And this is a picture from Hasselmann's 1976 paper, and I'm showing on the right some observations that I think kind of pose the problem he was out to solve. So these are, on the bottom, these are spectra, so showing the variability as a function of frequency along the horizontal axis of fluxes of latent and sensible heat into the ocean at ocean weathership India, which perplexingly is in the Atlantic. But you see that these fluxes are white noise approximately in time, which means that there's kind of equal variability across time. But if you contrast that with the sea surface temperature anomaly at Station India, you see a red spectrum. So this is a spectrum where there tends to be greater variability at longer time scales. And the framework that Hasselmann introduced was to argue that a simple model of temporally white atmospheric forcing with a stabilizing linear feedback in the ocean sufficed to generate this red spectrum from the white atmospheric spectrum. So this is kind of the paradigm of Hasselmann, but he also, of course, went on to say that there are other places where ocean variability might play a dominant role, so suggesting in places in fronts or ocean currents. And I think that in the intervening years, since this seminal set of publications, an open scientific question is where and to what extent the ocean and atmosphere are in this kind of Hasselmann balance. So where is the ocean behavior governed by local atmospheric fluxes? And this so one example of this is a lively debate over the past 10 years or so now, basically addressing whether or not Atlantic multidecadal variability, which is this variability that we see with a characteristic pattern in the North Atlantic in a period of roughly 70 years, whether ocean mechanisms are really necessary for that, or whether a slab ocean model, so again, just this notion of the ocean as an integrator of atmospheric noise, whether that suffices to describe that variability. So one example of a system that I'll talk about today that we believe to have both local and non-local atmospheric drivers is the Atlantic meridional overturn circulation, which is the name given to a system of processes and currents that are responsible for the meridional transport of heat, salt, and other tracers within the ocean. And this has long been an important summary of the ocean's role in climate. In the past 20 years, we've been able to observe it using, among other things, the rapid array, which is a set of moorings and current observations at 26 North. And when these observations first came out, they were a little bit sensational because we thought of the ocean and the AMOC as this sort of stentorian, very low frequency thing. And yet we saw variability across all timescales in the AMOC observations. And subsequently, people have picked this apart and found that the AMOC, like a lot of other climate systems, we can think of as a stochastic process. And so this is a quote from a paper by Wunsch and Heimbach 10 years ago. And they say that with the benefit of hindsight, the result is unsurprising. A system, the AMOC, with a long memory is subject to continuous small stochastic disturbances, which are decorrelated in space and time, and integrate to manifest themselves as a component such as the AMOC. So here we have a Hasselmann-like picture of stochastic atmospheric forcings integrated here across space and time as well, so having these non-local influences. And I think the state of the art for understanding the drivers of the AMOC variability is summarized by this nice paper last year by Laura Jackson and colleagues, which is basically trying to break down the stochastic AMOC variability into components due to wind stress and buoyancy forcing, with the notion that the variance then is going to arise from these components and then any kind of covariances between them. But there are still puzzles in terms of what the driving forces are between buoyancy and wind stress across different time scales, and also what atmospheric patterns might be associated therewith. So we're trying in a way to, we're motivated by this Hasselmann picture of the atmosphere driving the ocean. And so we're trying to step back and address this question, which is to ask, what are the dominant atmospheric modes and ocean pathways by which the atmosphere drives ocean variability? So next, I'll discuss some ways of answering that question that come from the ocean and atmosphere and contrast them. So this is the question we're interested in addressing. So in order to do that, it's helpful to think about what drives the ocean in the first place. And I'll say again that I'm adopting this framework of an ocean that is driven by atmospheric variability. We recognize, of course, that there are couplings and feedbacks that are important for some processes. But here we're focusing on processes that we think can be described by this atmosphere-forced variability. So from a model perspective, you can think of an ocean model state. And the way we force an ocean model is with a collection of boundary conditions: air temperature, wind stress, radiation, freshwater fluxes, humidity. Of course, we have boundary conditions from the bottom of the ocean as well. And you can think of these various forcing variables as being the controls in an airplane. And in fact, in state estimation, we do refer to these as the controls. So you can think that by adjusting your patterns of radiation or wind stress over time, you can adjust the trajectory of your ocean model, just like you would adjust the trajectory of an aircraft. So that's fine, and that kind of tells us how to drive an ocean model. But for this question of what quantities are driving variability, that's an inverse problem. And so we can address the inverse problem using the adjoint sensitivities of an ocean model. And I think this used to be a pretty esoteric topic. We do this using automatic differentiation, which is really you take your computer code and you send it off, in this case, to a company called TAF in Germany that specializes in this, and they send you back your 500,000 lines of Fortran that is just differentiated with respect to your control variables. And this is kind of taking up, it's becoming more and more popular. Automatic differentiation is a hot topic in machine learning. So it's also widely used in state estimation and parameter estimation. Okay, so what is an adjoint sensitivity? So we start out with some quantity of interest in your ocean model. It is any function of the model state. So for instance, here we might talk about the AMOC, the strength of the AMOC at 26 north. And we're interested in how that quantity of interest varies with respect to our controls. So in this case, this is a vector of our ocean model inputs, like wind stress. And so the adjoint sensitivity is the dx by du here, right? Is the partial derivative. How much will changing your controls change your quantity of interest? And there's a history now, 20 years or more, of folks using this not just for parameter and state estimation, but to actually do some science and learn about how the ocean works. And so these are some figures from a paper by Helen Piller and co-authors in 2016. So plotting the sensitivity of AMOC strength to zonal wind stress. And so what these maps show are at the lag, shown on the bottom here, 1 month, 3 months, and 1 year. If you change the zonal wind stress by the amount shown in this color bar, you are going to affect the AMOC by the amount here. So this is in units of Sverdrups per Newton. So if I give it 1 Newton additional wind stress in a particular region, I'm going to get out the commensurate amount of change in my AMOC. And so you can see that as a function of time and lag here, initially we start out with something that you might think is a Hasselmann type response, right? What the ocean wants at 1 month lag is for you to blow winds and generate transport across 26 north, mostly by Ekman transport. But as you start to get further and further back in time, you actually see more and more non-local effects. And so these are places where if you blow the wind even a year before, a series of Kelvin waves or advection can take the ocean and can transport through the ocean and change the AMOC. So you can see from this that if you think about then how atmospheric variability might project onto the ocean, you could see that a range of atmospheric variability might suffice to excite these modes within the ocean. But we can take this a step further and to say, well, let's assume that the atmosphere is white noise in time. So what is the pattern that most efficiently excites the ocean variability? So now this brings us to the literature. The 90s are just a great decade for this. These are called stochastic optimals. So this is, if we're in this Hasselmann type white noise forced regime, the noise with the spatial coherency of the stochastic optimal will be the most efficient at forcing variance growth within the system. Okay, so what do these things actually look like and how do we make them? You make them by, well, we have these patterns of adjoint sensitivity going back through time that tell you how you should excite the system at 1 month or 1 year, and we're going to stack them all together. And we're going to make a matrix, and we're going to compute a singular value decomposition. So this is basically saying an EOF-like analysis on our adjoint sensitivities. And what you get is a set of ordered pairs that tell you basically these O's here. These are the optimal patterns by which you would like to excite the AMOC variability using wind stress. And this is what the stochastic optimal for AMOC at 26 north looks like. So AMOC, so the 26 north is the dotted line here, and we see a combination of 2 mechanisms. One of them is this local, primarily Ekman transport excited thing that just lies right along 26 north. And then the second dominant feature that you might notice is along the western side of the African continent. And that's a place where if you excite Kelvin waves, they will travel right to the right in the northern hemisphere and then excite variability at 26 north. Okay, so you can think of this as what the ocean wants. The adjoint sensitivities are a recipe for how to excite ocean variability. In a way, it's a very specific request, and you can think of this as the ocean saying, okay, I want the G that's 2 octaves above middle C in order to give this kind of outcome. But then, of course, there's the question of what the ocean is actually getting from the atmosphere, right? The atmosphere doesn't care about our quantity of interest. To some extent, the atmosphere doesn't even care about a lot of ocean dynamics. So what does the ocean get? This is the question that is answered by the leading, or can be usefully summarized by the leading empirical orthogonal function. So this is the pattern, a way of diagnosing what pattern dominates atmospheric variance. So it's the same procedure. We're going to, in this case, take our sort of maps of atmospheric forcing, let's say wind stress in this case, and we can compute, again, an SVD, and we get these dominant patterns of atmospheric forcing. And so here we're doing this for wind stress computed from the echo state estimate, which I'll talk about more later on. And this is characteristic of the dominant patterns of atmospheric variability. They are large scale in space, and in contrast, stand in contrast to this specific thing of what the ocean might want. So I've shown you now 2 kind of perspectives on what might drive ocean variability. The first is a very specific recipe that comes from ocean dynamics. It's informed by what kind of ocean physics will excite your quantity of interest and wave propagation in the ocean. The other is just the fact of what the atmosphere is doing. And in a way, this second picture is kind of the history of studying drivers of ocean variability, right? We often talk about the role of the NAO or the East Atlantic pattern. The question that we're trying to address, or I guess this leads to a couple of points. First of all, is the leading EOF really the leading driver of variability in any ocean quantity? Also, does the leading stochastic optimal actually point to the leading mechanism for changing the ocean? And in general, the answer is no. So what we want to try to do is to reconcile these 2 approaches and to come up with atmospheric patterns that maximize contributions to ocean variability. So that's what we're going to do next. So we're going to reconcile these approaches with a new kind of principal components analysis. So here's the math slide. So we're starting off with this definition of adjoint sensitivity, right? This is our recipe for how to change our quantity of interest, x. And if I want, I can take this estimate of adjoint sensitivity and I can apply a finite amplitude perturbation to it, right? And so I can basically multiply this sensitivity, which I've written as a function of lag tau. I can multiply it with some little bump in my controls, right? Like rain a little bit somewhere or something like that. And if I sum that up over all of my lags, I get the resulting little change in my AMOC, right? And so this is kind of an estimate of how I can change the AMOC with my controls. That's fine. Now, what we're interested in is the variance itself, right? So now we're interested in the expected value of the square of these little changes to AMOC. So that's the variance of our quantity of interest, right? Here defined as AMOC. So if we take this increment, delta x, and plug it in here, what we get is a somewhat gory explosion. But what is essential to recognize is that this thing in the middle, which is a function of these various lags, is a space-time covariance of our control value. So that's basically saying, okay, this is how we think our wind stress and our buoyancy fluxes vary in space and time. And now we are saved by making the Hasselmann assumption of stationary atmospheric white noise. And this is a path that was trod by folks like Kleeman and Moore and Ioannou and Farrell back in the 90s as well. I've laid it out in kind of a linear way, but as always, this thing, I think it took probably David and I like 12 months to actually figure out what was going on. But what you end up with is something that basically you end up with a dynamics-weighted principal components problem. And so it says that if we want to find the atmospheric patterns that dominate ocean variability, we need to solve this particular weighted least or SVD problem.
So how do you determine what big N tau is? How many lags do you put in?
15 years. Basically, we look at the system and I'll show this in a little while too. So these adjoint sensitivities, after a while they go to 0. And it basically says that you can blow the wind in the year 2000 and the AMOC in the year 2022 is not going to care that much. So that's how we define that. So, and this is a sort of simplified view of this without loss of generality. We also did a detour to think about seasonality of variance, and the details for that are in the paper. But we ended up with a fairly straightforward result here. So I just want to summarize that the leading stochastic optimal most efficiently excites ocean variance. The leading EOF dominates the atmospheric variability. And what we're calling these EDFs, empirical dynamical functions, this is the atmospheric pattern that dominates ocean variability. The patterns are not correlated in time, but they may be in space. We are not the first ones to discuss this. This is known as balanced truncation in the control theory literature. Some nice properties are that when the atmosphere is white noise in space, we just get the stochastic optimals back. And when the ocean has no preference, then we just get back the EOFs. So those are kind of limit cases of this. Okay, that's enough dragging through the mathematical weeds. I'll try to demonstrate this next in a really simple system before going ahead and showing this in the MIT GCM. So I'm showing you first a sort of made-up stochastic system, which is one-dimensional with stochastic forcing that is smooth in space. So it kind of has this length scale associated with it, and Gaussian white noise in time. So here are just the first 3 realizations of this stochastic process that I made up. And for purposes of our problem, we also have some artificial adjoint sensitivities. So you can imagine the ocean, this one-dimensional ocean, has these sensitivities which are large and have a very short length scale and in only part of the domain, okay? And so this is meant to caricature this thing that we've seen in our ocean model, which is that the atmosphere has these long length scales of variability, and the ocean has this preference for short length scales in a particular place. So if I compute the leading EOFs of variability in this hypothetical system, what I end up with are these smooth, large-scale patterns that are centered on the center of the domain. They're actually very close to the Fourier basis. But when I compute these dynamics-weighted principal components, I'm basically combining the information from my stochastic system and my adjoint sensitivities. And so what we see instead are that the leading 3 dynamics-weighted principal components have been shifted to the left side of the domain, reflecting the fact that that's where the adjoint sensitivities are largest. Nevertheless, they still have the large length scales of the stochastic system. And then we can compute how much of the variability, the contribution to the quantity of interest, arises from the leading EOFs versus the rising dynamics-weighted or EDFs. And so that's what I'm showing here. So you can see that in terms of the variance of this hypothetical quantity of interest, the EOFs are going to slowly accumulate it. But the dynamics-weighted principal components capture most of the variability in just a single leading pattern. So they've been optimized in this case. These are the forcing patterns that might not have most of the variance of this hypothetical stochastic system, but are optimized to drive the quantity of interest. Okay, so let's actually take this for a real drive with a real model and see what we get. So the starting point for this, we're going to use the model configuration as well as the surface fluxes and adjoint sensitivities associated with echo. This is an ocean state estimate that runs from 1992 to 2022. It uses these adjoint sensitivities in a 4D VAR approach. So far I've said, well, imagine a quantity of interest, which is maybe the AMOC. What echo does is say, okay, our quantity of interest is just all of the model data misfits over the last 30 years. Excuse me, 30 years. And so they have an iterative approach to adjust the model controls, and what you end up with is a free-running version of the MIT GCM where fluxes, boundary conditions, initial conditions have been adjusted to fit a wide range of observations. And the model underlying this is a nominally 1 degree resolution MIT GCM. So here we're using, we've spun up this model for 4,800 years to avoid drift. We've adjointed the model and run it to compute sensitivities of, so this is the first quantity of interest I'll discuss. So we're talking about here annual mean heat content over the upper 700 meters of the subpolar gyre, which we've defined as this contour here in black that's south of Greenland. And the fluxes that we're using, these are our atmospheric controls, are 6 hourly resolution, and they are also inferred from the echo state estimate. So we can first discuss or show what the leading EOFs of heat flux variability. So I'm going to focus on heat flux and wind stress as the two atmospheric controls here. So I'm showing on the right-hand side here the EOFs and the principal component time series associated with the leading 3 EOFs of heat fluxes over the echo period over the North Atlantic. And so you can see in the top, it's kind of emblematic of all of them, and we have this kind of dipolar structure that's dominating in the North Atlantic, and associated with that, a strong amount of seasonality in the variability of the fluxes. And so I'm looking at anomalies about the seasonal cycle. So the seasonal cycle has been removed here. It would be very large, but just to show that this variability is much larger in winter. And we associate that with the presence of many more storms in the North Atlantic winter. So this seasonality is present in all of the 3 leading EOFs. They all have these characteristic large-scale shapes. And on the bottom here, I'm showing the squared singular values of the EOFs. So which is the point here that I'd like to make is that none of these leading 3 EOFs is capturing most of the variability. We really have a situation where there's a fairly large number of patterns that are responsible for heat fluxes in the North Atlantic over this time period. A qualitatively similar thing can be said for wind stress. We have these large-scale patterns. They're mostly focused in the North Atlantic. There's some seasonality to the cycle of variability, although less so than heat fluxes. And again, the cumulative power is suggestive of a relatively broad spectrum. So it's not like there's just one pattern that's capturing all of the wind stress variability in the echo state estimate over this period. Okay, now we get to look at the stochastic optimals. So as a reminder, this is the spatial pattern that the ocean would most like to see if you want to change the heat content in the upper 700 meters of the Labrador Sea. So the first one is kind of a no-brainer. It's basically the ocean saying, you would like to change the heat flux, the heat content. Maybe you should change the heat flux right over the place that you're interested in, right? And so this is this bullseye that's located right over the subpolar gyre. The time series associated with this stochastic optimal is worth looking at as well. And so you can see that there is a strong sensitivity that arises basically at 0 lag. That decays away slowly. And then superimposed on that is a strong seasonal cycle. And this seasonal cycle arises from this mechanism described, again, 50 years ago by Henry Stommel, known as Stommel's demon. The notion, which is kind of modeled after Maxwell's demon, the notion that if you want to have a persistent heat anomaly in the ocean, you need to sneak it below to get it below the permanent thermocline. And in order to do that, it's best to do it in winter when mixed layer depths are deepest. And so that's why the sensitivities that we see are much greater in winter than in summer, because that heat content anomaly is mixed through the water column and can persist over a scale of years. So by contrast, you'll see that this leading pattern here is really capturing a lot of the sensitivity. So this local heat flux anomaly, maybe a Hasselmann type response, is seems to be most of the story. And then the wind stress stochastic optimals are different. So here we can see once again this role for remote forcing, the fact that we have a lot of sensitivities around the northwest corner in the North Atlantic where the Gulf Stream meets the subpolar gyre, but also along the western coast of Europe and Africa, and this is as well as the equator. So these are the equatorial and coastal Kelvin wave mechanisms that can lead to heaving of isopycnals and heat content anomalies in the subpolar gyre. Okay, so those are kind of, again, the recipes that we get from the ocean and then this behavior of what the atmosphere is doing. When we do this dynamics weighted principal components, what we see is a collapse of the potential mechanisms of the atmosphere down to a leading mode, which you can see here in the black, captures the vast majority, over 90% of the variability in subpolar gyre heat content. And this is worth contrasting with the leading EOFs of heat content variability, which are not nearly as effective at driving the variability in the model. And so you can see at the top, this dominant pattern has a different shape. It no longer has this dipole structure that we saw in the first EOF. This is basically the North Atlantic Oscillation. This is correlated at a 94% pattern correlation with this sort of canonical definition of the NAO. We see something quite similar for the wind stress EDFs as well, that although it's not as striking as with the with the heat fluxes, that again we have a pattern that is most responsible for the wind stress contribution to heat content variability in the subpolar gyre, and is once again correlated, once again at 94%, with the canonical NAO. Okay, so that's fine. I guess I'll opine here briefly. So we've done all of this, and we have come up with something that has been studied again probably for 50 years, right? You're interested in what drives subpolar gyre heat content variability. It is the NAO, right? But I think there's something to be said for that. That the NAO is the dominant pattern of wintertime variability in the North Atlantic. But here we've basically just said we're interested in what drives this particular ocean quantity. This ocean quantity is sensitive to wintertime features, and it's sensitive to variability that is ongoing in that place. So in a way, while in this case we have kind of rediscovered something that's been around for 50 years, we treat this as a useful proof of concept, right? That you can go in with an ocean quantity, and by virtue of time scale or geography, it can pick out a relevant mode in the atmosphere. Okay, so far, this analysis has been done in the space of adjoint sensitivities. So we're trying to find these optimal structures, but they've been done in this linear dynamics approximation that we get from the adjoint sensitivity. So now we're going to use echo as a sandbox to play around and see what happens when we start pushing and pulling on these modes of variability that we've found. So the first thing that we can do is to omit a leading, I apologize, I've used WPC and DPC interchangeably. So the echo state estimate at the end of the day is just a forward simulation of an ocean model, and it is forced by these boundary conditions. And so what we can do is we can take these boundary conditions in space and time and just regress out these dominant patterns that we've seen, or that we've derived, and then see what happens to the ocean state. And so this is what we've done here. And these spaghetti plots are going to show a progression of removing more and more of these dominant modes as we go from top to bottom. So at the top, what I'm showing in the black is the full echo state estimate of ocean heat content variability in the subpolar gyre region. And in the blue is what we get when we perform a linear reconstruction using the adjoint sensitivities. So I apologize, this is a useful subtlety that I should have mentioned earlier. So when we make this adjoint sensitivity approximation, we're talking about a derivative, right? And so that is a local derivative. It's a tangent to the variability that you might see in the ocean. So, okay, maybe it's good that I didn't go into that too deeply. But here, we're basically just showing that it's a sanity check, that this linear approximation that we make that's in the blue actually gives us a pretty good representation of what the full nonlinear model is doing. Okay, so then the second panel here is showing what happens when we take the NAO out of the echo state estimate, or something that looks a lot like the NAO. So the first thing that happens is you get actually a big trend in the amount of ocean heat content in the subpolar gyre over the echo period. And there's a couple of things that could be responsible for this trend. The first one that seems most likely is that we are using this flux-forced model. And we've had to do this to be very careful to separate contributions from winds and buoyancy, so we're not having to run through bulk formulae. But what we're able to do is basically decompose this into two pieces. One of them is a linear trend that results from this kind of secular change. So if we take out that trend, what we see in both the linear and the nonlinear model are heat content variability that is much quieter on these interannual timescales that we're interested in. So when we take out the NAO, we get a long-term trend. We also, though, and this is kind of the thing we are most interested in, see that the variability in heat content goes way down. So that is an argument that this leading mode is also important in the full nonlinear model. I won't describe in depth what goes on. Basically, we know that these second and third modes are not as important. When we take them out of the linear model, they don't, similarly, they don't make that much of a difference. And eventually, we do see even more nonlinear behavior later on. Okay, and I'm just going to show this for heat content variability. Okay, so what we've argued then is we have this dynamics weighted principal components analysis. We can isolate these mechanisms that are most important for driving ocean quantities. We can pull them out of either a linear or a nonlinear model, and they appear to, to be driving a lot of the variability by those experiments. The other thing we can do is another kind of way of messing with the state estimate, right? So instead, in this case of regressing out the forcings, we can add additional forcing into the echo state estimate and look at the anomaly of the state estimate when you run it with an additional perturbation relative to running it without. So this is what we're doing here. This is the perturbation that we are making. This is the leading EDF. And this is then the evolution of this perturbation through time at 3 months, 12 months, and 3 years. And in the top panel is the evolution of the ocean heat content anomaly in the subpolar gyre. So if we flick the model for 24 hours at t = 0 with this heating pattern, we see a very Hasselmann-like response in this case, that we have this initial heating, it goes into the ocean, and it basically just decays away through time with some overshoot on interannual timescales. By contrast, when we do this for the wind stress, so here we're going to take this leading wind stress mode, blow the wind for 24 hours, and then watch the evolution of the ocean through time. We again see this delayed response. I say again because this is what we also saw in the adjoint sensitivities, that you have an initial heating, and then it persists through time, and it's associated with negative heat anomalies to the north and south, which is suggesting a role for ocean heat convergence from these regions that are proximal to the subpolar gyre. So this is something where there is clearly, by virtue of the timing of the signal, a role for the ocean in maintaining an interannual heat content signal. Okay, I'm mindful of the time, so I will just make a brief advertisement of an application of this that David led to decadal AMOC variability. So in this case, we're using the same MIT GCM setup, but where our quantity of interest is no longer heat content, but the climatological, the AMOC transport at climatological maximum depth across several latitudes. And so this is just showing that the model that we use to compute the adjoint sensitivities and the echo AMOC overturning stream functions are qualitatively similar. So there's a punchline here, so I'm going to get quickly to the punchline. When we compute these EDFs for the buoyancy forcing, they reveal that the decadal AMOC strength in both the subpolar and subtropical gyres are also dominated by heat fluxes similar to the NAO. So we've gotten really good at rediscovering the NAO. This is kind of interesting, though, because this is basically saying that the NAO buoyancy fluxes are important for AMOC changes both at 26 north and at 45 north. And if we, and we can do a similar perturbation type experiment, and you see that this AMOC anomaly is primarily sustained by the establishment and maintenance of a zonal density gradient across these sections that has to do with the advection of a heating signal by the model's deep western boundary current and Gulf Stream and North Atlantic current. The wind stress picture was different. And so once again, so I'm showing here the forcing, the leading EOF, and then the stochastic optimal. And what we see is that at different latitudes, we have two different patterns that are responsible for the wind stress-driven component of decadal AMOC variability. And we tried pretty hard to relate these. So this is at 25 north and 55 north, these two rows. We've done pattern correlations with the NAO, with the East Atlantic pattern. We'd be happy to do them with your other patterns. But these appear to be two atmospheric patterns that are uncorrelated with other variability and that are most important for driving the wind stress component of AMOC variability. And they do different things. The first one generates a heat anomaly in the subpolar gyre, and then subsequently the evolution, again, so we're thinking about this zonal density gradient as the thing that really dominates or drives AMOC change. So it behaves a lot like a density response very similar to the heating anomaly that we saw. But at lower latitudes, there seems to be a different mechanism at play, that we're actually exciting the Rossby waves that are excited off the coast of Africa and propagate, combine with the advection of a density anomaly, this time through the Gulf Stream and North Atlantic current. And it's that combination, David calls this the toothpaste tube, of white and blue anomalies here that persists on decadal timescales and gives you that AMOC variation. Okay, so we have models, and we can compute these adjoint sensitivities, and they tell us something cool, which is what the ocean wants from the atmosphere in order to behave in a certain way. But we have to think about how the atmosphere projects onto those patterns. And through this approach of balanced truncation or dynamics-weighted principal components, we can derive atmospheric structures that dominate ocean variability. When we apply this to the problem of annual mean subpolar gyre heat content, we find that the NAO, both in heat fluxes and wind stress patterns, is most responsible for driving variability through a combination of passive and active roles. When we apply this to decadal mean AMOC strength, we find again that NAO buoyancy fluxes dominate, but there are these two patterns of wind stress that appear to play leading roles in the subpolar and subtropical gyres, again moderated by ocean pathways of variability. I've shown this for the atmosphere and ocean, but in general, if you have a system that is excited by variability in another, I think this method is applicable. Having an adjoint will save you a lot of time, but you could just as well run perturbation experiments to compute these sensitivities on your own if you have core hours to burn. And there are lots of caveats here, right? So this is 1 degree model dynamics that we're using. It's ocean only, flux forced. There's a whole field in the world of EOFs thinking about the significance of EOFs. So in a way, we're inheriting problems both from the model and statistics. So I will say that there will be a forthcoming postdoc advertisement to work on this on a future project funded by NSF and NERC. So send me your great applicants, please, and I'm happy to take any questions. Thank you so much.
Okay, good. If you have any questions in the audience, just raise your hand, and you can just speak. Okay, go ahead.
So you've talked about changing the heat fluxes, and then you've also used the word buoyancy fluxes quite a bit. So what have you been doing with the fresh water forcing? Because in the high latitudes, the fresh water changes density often more significantly than heat does. So when you've taken these modes out of the forcing, for instance, in echo, have you changed the freshwater forcing at all?
No, we have not, and I may have gotten a little loose in using those two things interchangeably. Early on, we did look at the sensitivity to freshwater forcing for these quantities of interest and found that it was relatively small, which is what led us to the heat fluxes and the wind stress approach. But we're definitely interested in looking at that, for instance, for salinity anomalies and other places. But it just appeared that it wasn't as important for heat content and AMOC, decadal AMOC.
Because in the NAO, I mean, that changes the where it rains sort of significantly spatially across the North Atlantic.
Yeah, and so there may be correlated pieces of that variability from the other piece of the buoyancy, the freshwater, that we are not seeing. Yeah, that could be. But in this case, it appeared that these two terms were dominant, which is why we focused on them.
Okay. Yeah, Katie, go ahead.
Thanks, Dan. I'm curious about your experience with the automatic differentiation. So you mentioned, sending the code off. How did you find the company? How did that process work?
So this is, the company was basically founded in part to do this work, and that was 25 years ago out of MIT, and they've kind of, this model, and the company does a lot of things. Working on this model is one of them. In a way, it's kind of a troubled relationship. But it is arcane. I feel like it's a club of people who can do this and who know how to massage things the right way. So I think the tool is really powerful. I think there's a lot that can be done in this space with much more open source tools. And I'm excited to talk about what those might look like.
Yes, we have a few hands. Clara, and then who?
Yeah, thanks, Dan, so much for your talk. I was just interested if you might extend this work to then ask what are the EDFs for the NAO or that come from AMOC, and maybe part of the reason why the NAOs comes out is also that it's responsive to AMOC, and maybe that's part of the answer. So not just this top-down Hasselman view, but actually invoking some importance of two-way coupling.
Yeah, I think that's a really interesting point, and David and I have talked about this some. Why is it that the ocean adjoint sensitivities look so much like the NAO, right? Is there something special where those two have settled on that? So yeah, I'd be really interested to look in that question, into that question. I agree. It is much easier just to treat the atmosphere as a static hiss. Yeah, there's cool work to be done there, I think.
Okay. Yeah, go ahead.
Oh, thanks. So yeah, wind stress results are somewhat surprising to me. So I guess it's different from previous studies stressing, NAO-related wind stress is important for AMOC driver, etc. So can you say a little bit more about this wind stress results, and can you also say about relative contribution between buoyancy forcing and wind stress forcing for the AMOC variable?
Yeah, so so these patterns are more effective than the wind stress patterns associated with the NAO at driving AMOC variability. And in our opinion, these results differ from previous studies because we're trying to take this backwards approach. Instead of taking NAO wind stresses or other patterns of wind stresses and looking at their influence, we're trying to figure out which patterns most influence the ocean. So, in a way, this is kind of one of the things we are hoping to see, right, is the power of this approach to find a new atmospheric mode. That said, I would caveat that with, these modes, as we've defined them, are patterns in the atmosphere. They're modes insofar as, and I see Cecile, mode can be a four-letter word. It is uncorrelated with any other variability over the echo period, right? And that is 30 years of fluxes. So one thing we haven't done was to try to apply this, over a much longer period of time and see to what extent it is independent over longer periods. In terms of the contributions of wind stress and heat content, I don't know the exact relative contributions of these things. I think heat content or heat fluxes are a greater contributor for the heat content variability piece, and they are on more of an even footing on the AMOC, but I have to get back to you on those exact numbers.
Yeah, I think actually there is a question in Slido. It also asks about like longer time series experiments. Maybe that's similar and something that you want to do. So this is a question from Ali, and he
Yep.
asks, yeah.
Yep.
If you do longer.
Carry them out for longer time series. Yes, I mean, the tricky thing that I'm still not sure how to do is how to perturb a coupled model. You want to do it in a way that is consistent in both the atmosphere and ocean. And so here we're kind of, we have this island where we're saying, well, we think that a lot of this variability is forced and we can safely do it in an ocean-only capacity. But yeah, I think if there is a way, and maybe folks know, of perturbing a coupled model in this way, then I think that would be a really nice demonstration.
Judy, do you still have your question?
It's okay.
Okay. All right. So how about we go with the question online first, and then we go to Steve. Yeah, so this is from Cecile.
Great, I'll read it out. EOFs, dynamically weighted or otherwise, are orthogonal. Have you tried anything like a linear inverse model which yields mode not confined to be orthogonal? You can then use fluctuation dissipation to diagnose the stochastic variability, find normal growth. We looked into limbs for this, but it was in this sort of dark wandering period in the wilderness of trying to figure out an approach that worked. I mean, so in this case, these are EOFs. They are orthogonal in time. They are not orthogonal in space. And so one of the things we played around with is you can be orthogonal it's basically which dimensions you want to be orthogonal in. And so here we settled on being orthogonal in time because we wanted this, sort of this modal property, but we wanted the flexibility, as you're saying, to be orthogonal in space as well. Non-orthogonal in space. So maybe there's a way of extending that with the limb. I mean, at some point too, I think there might be overlap between a linear inverse model and the adjoint sensitivities you get from a linearized version of the model. I'd have to think about that more.
We have a question here.
Again, so I got a little confused. You showed the EDF for subpolar heat content. It seemed to look very similar to the EDF for decadal AMOC that Duffy then did a perturbation experiment with. I'm curious, about how the loading is focused over the Labrador Sea, and I'm curious, how does ECHO perform in that region? Does it have bias mixed layer depth? Have you compared it to OSNAP? And would that give you confidence in weighing in on the debate of Lab C versus Erminger C as far as what drives AMOC decadal variability?
Yeah, so we did find a very similar pattern. And, in a way in the limit when there is only a single pattern in the North Atlantic, you would expect to recover that basically for any ocean quantity of interest, right? It kind of has to be the sole source of variability. In this case, because both the AMOC and heat content are especially sensitive to wintertime fluxes, I think that's why you pick out the strongest wintertime signal, which is the NAO. The MIT GCM that we use is a 1-degree model. I couldn't tell you off the top of my head how it compares to climatology. I mean, it has been fit to observations, but in a way that is prioritizing a global fit. So that is not to say that there couldn't be an outstanding bias in, for instance, its winter mixed layer depth. Furthermore, although we are able to extract the NAO and tamp down a lot of variability in the model AMOC. Well, no, actually, I will not caveat it that way. I think we'd have to really dig in and argue that the processes that you see in the observations and the MIT GCM are similar to authoritatively weigh into that debate. Because otherwise, maybe it's just another 1-degree problem.
Okay, I saw a few hands over there in the back. Yeah, go ahead.
Yeah. So to follow up on Claire's question a little bit, and to get at another 50-year-old question, it's always, is the ocean forcing the atmosphere, is the atmosphere forcing the ocean? I mean, you've set up this great methodology. Could you run it in the opposite direction? Could you actually take an adjoint of the atmosphere, look to see what the atmosphere wants in the North Atlantic, see what the ocean's giving it, and come out with the same kind of analysis?
Yeah, you could. And we've played around with this a little bit with Jesse Vance, who's a postdoc. So he was interested in air-sea fluxes of CO2 in the Southern Ocean, and was doing these perturbation experiments, basically, releasing an atmospheric passive tracer from different sectors around Antarctica, and seeing where they went and how they influenced, hypothetical airborne observations. And so that's fine. You're interested in what your observations are going to see somewhere over McMurdo. But you need an additional piece beyond just these kind of Green's functions, which is, well, where is the ocean actually fluxing CO2? So it's a similar problem of thinking about the variability, this time in air-sea fluxes of CO2. So that's very clearly a system in which the first order of the ocean is forcing the atmosphere. If there are other examples where you could do that, I think you could run a similar experiment. You wouldn't even need necessarily an adjoint of the atmosphere if you could run these perturbation experiments.
Yeah, go ahead.
My question was in a similar direction. So Hasselmann truncates the scales of interest at the synoptic scale and goes to everything larger, because that's what he could do, right? And you consistent with that by using a 1 degree ocean model and 6 hour forcing. If you would do the thought experiment and include the mesoscale in the ocean, that is way more energetic, and there's evidence that then the mesoscale actually forces the atmosphere, do you think that would substantially change your answer?
I mean, the tack that we've taken is that there are ocean quantities of interest that are, to first order, dominated by stochastic atmospheric contributions. So, I mean, one way of posing this could be to say, if we had an ocean model that was mesoscale resolving, and we were still interested in one of these large spatial, long temporal scale quantities, then, that is a test of the Hasselmann hypothesis, I guess. Is within that model, is that still something that is primarily stochastically forced? It becomes non-trivial to compute adjoint sensitivities in an ocean model that is like that, because it becomes highly nonlinear because of all these mesoscale eddies that are running around. Which is to say, I may never be able to test that question for you, so maybe I'm safe. But no, I think we have to think carefully about the dynamical regimes that we think might obey Hasselmann. And then maybe, similarly, I guess you could define a quantity of interest which is sitting inside a mesoscale eddy, and then you're hopelessly coupled, right? And maybe this approach would not work.
I just want to comment, Hasselmann is not just the highest frequencies, it's white noise. It's all time scales. It's just no preferred time scale.
Yes, but he somehow ignores that there's a mesoscale in the ocean.
Yeah, understood.
Yeah.
Yeah, he's not. He's concerned about this local feedback. Yeah.
All right. We've actually got a lot of questions for Dan today. A lot of things to think about. Let's thank Dan again for today. I also want to make an announcement about our seminar next week. And starting from November 7th, like next week, we want to join like a CGD cafe with a CGD seminar. So the CGD cafe will start at 10:30. And then it's still at the director's office, and there will be coffee and cookies. So that's more like a social thing, platform for people to get together. And then once you're done with the CGD cafe, so come over to the CGD seminar, which will actually start like 10 minutes later, so that you get a little bit more time to come over and join us in this main seminar room. Okay, so starting next week, we will have coffee and cookies before CGD seminar, and we will start 10 minutes later. That is at 11:10. All right. Thank you so much. Thank you. Happy Halloween.